And Brian?
All right. All right. So we talked a lot about, design considerations, in terms of properly designing the sensor, making sure you're selecting the right components, the right materials, you execute the design. We're going to touch on a few extra things we do during the manufacturing process to try to optimize performance even better. So one thing that's unique to Interface is moment compensation. If you come across any data sheets for any of our load cells that has a side load or eccentric load sensitivity spec, that means it's a moment compensated load cell. So all of our LPs are going to be moment compensated. Our MBI that we referenced earlier, mini beam, as well as our SPI, which is a single point load cell, also goes through moment compensation. The minis are a little bit different process, but fundamentally still achieve the same thing. And that is that we will go in and actually adjust the load cell as necessary to ensure that it meets a certain spec when subjected to a pretty terrible off-axis load. So as depicted here, there's an LP bolted down to a base. If it's an 1100 or a 1600, that's going to be a base it ships with, for example. Otherwise, it would be a representative base, gets bolted down. This is before we put the diaphragm covers in, so the gauge cavity is exposed. Every unit, of course, is serialized, so the operator will load up that unit. It'll say, this is an 1100 series. This is the moment spec that we need to hit. And the operator then applies a pretty substantial load to it, much worse than would typically be seen in a proper application, at least. And we'll actually move that weight around 360 degrees and see how the zero responds to that. And then through mechanical adjustments of the beam, we'll ensure it pulls it within spec for that unit. So the goal here is that you can imagine almost an inverted cone coming out of that load cell, that as long as your load is applied within that, you're going to get very accurate axial measurements. So this is a very labor-intensive step that Interface does for every load profile, but this is how we can guarantee it meets our side load sensitivity and eccentric load sensitivity specs, which means you can throw it into an application and it's just going to work. And that's why people that have used it keep coming back for more of these. So next slide. This is a good pre and post snapshot of a typical load cell. Next slide, please. There we go. So here's a 1220 50K. The blue plot is the pre-moment. So every unit gets checked before. It's a good way we can check and make sure that the gauges were applied, where they should be, and should have good linearity and hysteresis further down the manufacturing process if it hadn't already gone through pre-cal. And so the blue line is the initial, if you will. The yellow is after moment compensation adjustment. So key things here to note are, one, the reduction in overall error, which is a small amount, but it's a pretty big reduction from pre and post, but also the number of times that the zero balance passes through zero. It went through 2 previously, whereas after a moment, if I can count, 1, 2, 3, 4, and it hovers very close in between there. So what that means now is this load cell has several neutral axes where it's completely insensitive to off-axis loading, which is pretty significant. So again, this is how you can have confidence that if you use one of these low profiles, you're going to get good results in your test. Even if you have, let's say, a long horizontal load string run, you got actuators hanging off of things. Again, sometimes even with support, you still can't quite neutralize. An LP is not going to care in most cases. And we have some customers that really want to know where the neutral axis is. And because we have full traceability during the manufacturing process, we can actually provide a chart similar to the one on the right there that says here, based on the connector, this is where you want to orient those side loads if you can't reduce them. So again, this is something we do on every single low profile, and we make more of these than anybody else in the world. So just a little bit of special that makes these perform better. Next slide. Because we test every unit, you're going to see a couple things on our data sheets where we have a max rated load, but then we also have a max error. And it's not just a theoretical max on the LPs. That's a guaranteed, again, because every unit's gone through moment compensation. And you can see tighter specs for some of these depending on the model too. So, all right, next slide. All right, so temperature compensation. Jacob's done a great job to talk about how temperature affects gauges and things we can do. I think it's important for everyone to leave with an understanding that temperature change around a sensor is going to impact 2 things. It's going to impact the zero balance, right? So that can impact your resulting measurement after you apply load, but it also impacts how much output you get from the sensor. The effect on those can be positive or negative, but it is good to note that it's repeatable. So if you were to take a sensor, run it through an oven, you'd be able to characterize exactly how sensitive it is. But like I mentioned earlier in the presentation, you got to be careful. If it's part of a mechanical assembly, every mechanical joint is going to respond differently, different items in it, right? So it can result in a different applied load. So always best characterize in situ. But how do we address that? Well, as Jacob said, the span adjustment is done from a batch standpoint on the gauges. So we'll basically qualify the batch of strain gauges to within the spec for the particular material they're going on. So whether it's an aluminum unit, whether it's a steel unit, stainless steel, we're going to make sure the batches are properly span tested for that. And then the zero test, this is something we have to do on every single unit. So every load cell that we put together, every time you complete a bridge, you've got to run it through and see exactly how the zero responds to that. So next slide. So as we mentioned, thermal response on output, we'll spec it as a % of reading. So it essentially just affects that slope. We do what we can to batch qualify, to choose the right gauges, depending on the desired temperature range or the material. But as mentioned, when interface proprietary string gauges are used on most of our product there, we don't have to add mod resistors to the bridge to further compensate. So you end up with a fundamentally simpler bridge, less components and to respond to temperature change, but you don't also then have more output. And that's how most of our sensors are 4 millivolt per volt, because we don't have to add things that reduce that signal. So next slide. Now, as far as temperature comp on zero, again, this is something we do on every unit. We do cold to hot versus some people just doing room to hot. So you end up with a much flatter curve over a wider range. But also, it's good to note that when we do compensate, we don't just adjust and ship, we adjust and verify. Most competitors will put the load cell in, see how much adjustment needs to be done to a bridge, and then ship that unit out, where we run it back through a second time and verify. So again, a little more extra labor, a little more extra cost, but we want to make sure we're delivering the best product we can. And of course, we have full traceability on every unit that goes through the floor. And we can also, of course, do custom ranges, whether it's a customer, a specific comp range in terms of where you want it compensated for, or if it's a matter of doing even span testing. We can potentially do that too and provide actual thermal response to the span. We have some force limits depending on what our ovens can accommodate, of course. But so what does this mean? Well, here's a couple examples, just how tight we can control temperature. Again, our proprietary gauges allow us to really tighten up these specs compared to what you'll find on most force sensors. On our 1100 series, which is our precision model, we're down to 0.0004% reading, or rated output, excuse me, per degree F. So even a 100-degree swing on 1100 series is going to be 4 pounds on a 10,000-pound load cell. So even our 1200 series load cell with 0.0008, again, if it's a 10K load cell, you're talking about an 8-pound error across 100-degree temperature change. So you really don't need to worry about temperature error when it comes to an interface low profile. Why does that matter? Well, oftentimes if it's used somewhere outdoors, especially if you've got the sun working across a test stand, that can make a big difference from early morning to evening or to the middle of the day, excuse me. But again, with an interface load cell, we were able to just control not only the gauge, but the bridge behavior at such a level that it almost pulls that error out completely.
Yeah, I'm glad you mentioned the bridge level, Brian, because the connections that you have in your bridge definitely matter. So if you think about if you had 3 times the wire connecting one leg of the bridge and temperature changed, you could definitely see how the change in resistance of those connecting wires would be 3 times the amount in that leg. So that's very important when considering the assembly of a load cell. You really want to position your gauges and take into account the wire length that you're using to connect your gauges and your bridge. And I think I saw a question here about if I'm operating at constant temperature that is outside the specified compensation range, will the output be as accurate as long as I first zero the output? And that's accurate, yes. So if you go to a temperature and you're able to zero it out, or you know that that's the new zero, from there you'll have accurate readings. The issue is if there's temperature changes and you can't compensate, right? So maybe you're loading as your temperature changing. That's when temp comp really comes into effect. And like Brian mentioned too, we do plenty of custom range temperature compensations.
I would add to that that you're referring primarily to the zero balance, right? So
Yes.
you do need to take into account the change to span. So if you are able to apply a known load at that elevated temperature, at least you would know how the span has been adjusted. Now we can give you a calculated value as well if necessary, but if you have the ability to do in situ cal check, it would be very repeatable and consistent. And excellent question that, if you can get your test set up to the elevated temperature range and zero it, now you've removed any temperature effect to zero, right? Because you've already teared that value out essentially, or that shift out. So good question.